Okay, so we have talked about the polymerization processes and talked about the bulk polymerization reactions. And bulk polymerization requires the monomers and initiators only. Okay? Therefore, there are some advantages and disadvantages of this bulk polymerizations. If I remind you, the advantages of this bulk polymerization is that you do not need to recover your solvent. So this is very simple process and a cheap process, but you have to be very careful about the temperature control because the polymerization requires a very high exothermic reaction. Therefore, your abrupt increase of your temperature during the polymerization reaction is a very critical issue and should be very well controlled in this case. Examples of these bulk polymerizations are the polyvinyl chloride and the polymethyl methacrylate and polystyrenes. And I told you that this abbreviation is a general purpose, the polystyrenes. And solution polymerization is very similar to bulk, but you have added the solvent here, so that the process will be much more easier to conduct in terms of the temperature control, because temperature exerted from your reaction system will be dissipated to the solvent, and the solvent, of course, does not increase the temperature of your reaction system very abruptly, but it's slowly, so that you can take your heat out of your reactive system by adding the surroundings, the environments, okay, like water jackets or the cooling medium around the reactor, so that you can control the temperature of your reaction system sufficiently. Okay? But one of the issues is that the chain transfer to solvent, okay? Chain transfer to solvent. As you have already know about this chain transfer section, there are many possibilities of a chain transfer during the chain cross polymerization reactions. Therefore, you have to be very careful about this solvent chain transfer. And as I mentioned to you the other day, the recovery of the solvent is an issue too. Okay? You cannot discard, you cannot make the solvent out of your system and discard it to the environment. Right? You have to recover those solvent and have to reuse them to the system to be economical process. And the second issue about the solvent is that environmental issue. Okay? You cannot vaporize those solvents to the environment or air, and it should be very highly controlled in order not to harm the environment in this case. Therefore, the solvent is a critical issue. You see the other day, the Samsung Electronics are very keen to know about the industrial safety, to the diseases that was held from their factory, and I think the cause of that the disease is sometimes because of the evaporation of the benzene. Okay? The benzene might be the very carcinogenic solvent. So the recovery of the solvent is really a big issue in the industry. Okay? So you have to be very careful about the recovery and the environmental issue and the safety issue and health issue in these cases. Assuming that you solve this problem, you can make the polymers such as styrene, butadiene, and styrene plastics, and butyl rubber, and other polymers like the naphthalene, the polymers, and so on. And so you can make many types of the polymers out of this solution polymerization reactions. These are just an examples, and I think you can make the other many of the other the polymers like polystyrenes, the rubbers, acrylonitriles, the PMMA, and others using the solvent processes. We have another two heterogeneous systems. Okay, heterogeneous systems. The first example is about the suspension polymerization reactions. Okay. Now, when you have monomer and initiator, okay, and these monomer and initiators are suspended in water system or aqueous system. In other words, if you have a water, okay, if you have a water and you put your monomer, which is not soluble in water, and put the initiator, which is not soluble as well in water, and if you can add the detergents, okay, then you make some sort of a suspension like this. Suspension. It's very similar to emulsion, but what we call the suspension is the size of the droplets are larger than the emulsions. Okay? So emulsion polymerization and the suspension polymerization is different in terms of the size of your droplets. Okay? Size of your droplets are a little larger than emulsion polymerization, which we will talk about later. Okay? Now, so when you mix your when you use your mixer, okay, in your household, perhaps you put your water, okay, and you add the oils, perhaps oils, and if you mix very rapidly again, then you may make a little bit of droplets of the oil and the water. Okay? This is fairly similar to what's happening in those mixers. Mixing the aqueous system and the organophilic systems together, okay, along with some sort of detergents, then you may make the some type of the droplets like this. What you can see here is that in this case, this is the detergent, and you may have the hydrophilic the circular items outside of this the droplets, whereas this is attached to one of the droplets. Okay, these droplets are surrounded by the detergents, and inside of those the droplets, there are something happening. Okay, something happening where your polymerization is proceeding inside of these droplets. Okay. Okay. So this is what we call the suspension polymerization reactions. Okay? You have initiation, propagation, and termination. Okay, all those mechanisms, even the chain transfer, would be happening inside of these droplets. Okay, so the polymer is formed after forming the suspension. Therefore, we call this as a suspension polymerization reactions. In terms of the kinetics, this is very similar to the bulk polymerization reactions because you have the initiator and the monomer and the polymeric radicals. Therefore, it's very similar to the bulk polymerization reactions, and so on. So, shear means mixing. Okay, shear. If you have a very high shear stress, that means that you have a large stirring or the mixing. So by mixing those monomer, initiator, and suspending agent, which is the detergents, and suspending medium, which is usually the water, then you mix in a very high speed, then you can form the polymer inside of those droplets of your monomers and so on, okay, with the others. Examples of those suspension polymerizations is that PVC, but suspension polymerized polyvinyl chloride and polymethyl methacrylate, polyvinyl acetate, the milky, those milky polyvinyl acetates, or milky polyvinyl chloride suspension. The milky polymethyl methacrylate are the examples of the suspension polymerization reactions. Finally, we can talk about the emulsion polymerization reactions. You have your monomer, initiator, emulsifier rather than suspending agent, and the water. Okay? So emulsifier is usually a detergent as well, detergent or the surfactants. Okay, so surfactants, and depending upon how many the hydrophobic layer that you have, hydrophobic methylene units in your detergents. Okay, in your detergent, what you can see is that you have your hydrophilic layer on the bottom. If you take a look at one of this line, you have many methylene units, and then at the end of your chain, you have your carboxylic acid or sulfonic acid with the counter ions, okay? Like a sodium sulfonate with the long chain. Long chain means that the methylene carbon unit number of those carbons might be 12 to about 16. Sometimes lauric acid or stearic acid. Okay? So you have many methylene units. These lines are hydrophobic, regarded as hydrophobic, whereas at the end of your chain you have your carboxylic acid or carboxylate ion with the co-ion such as the sodiums, okay, is embedded at the end of your chain, and depending upon the type of your detergent, okay, and also the type of your systems, we have the system here, and very important thing is that to form the emulsion, you have to have a water-soluble initiator, and water-soluble monomer instead of organophilic monomer in the case of suspensions. Okay? So these all of those systems, monomer, initiator, water, and emulsifier, are mixed together to form very small emulsion or micelles. We call it as a micelle. The size of those micelles are very small. Those droplets are. It's very similar to the suspension, but the size of those micelle is less than 100 micrometer, I would say. Okay, right? It's very similar to the suspension, but the size of those micelles are very small. And in the emulsion polymerization reactions, we have a critical micelle concentration. Okay? I'm not going to go in more details, but if you take a look at the colloid chemistry, you will see those CMC, the critical micelle concentration. So the micelle is not forming in every concentration, but you have a critical concentration to form the micelles. Okay? Anyway, in each system, you have specific CMC to form those micelles. And inside of those micelles, you have the monomer. You have the monomer here, and the monomer, of course, will be initiating. So the initiator is outside of your system, and it's diffusing into the monomer, and it starts to form the polymer as we have seen in the suspension polymerization reactions. So inside of those micelle, you form the polymer, and it's the same as what you have seen in the suspension polymerization reactions. Okay? Now, in this way, we can have a very easy control of the molecular weight and form the polymer, and the kinetics follows the what they call is a Smith-Avant kinetics. Again, I'm not going to go in more details about this, and you have many of those examples. Okay? The PVC, ABS, styrene, butadiene latex, polybutadiene latex, all of those rubbers, styrene butadiene rubber, and neoprene butadiene rubber, stuff like that. So the rubbers, mostly the rubbers are made by these emergent polymerization reactions. Right? So all of those, the polymerization reactions, have to be made at least the following one of those four polymerization processes, starting from bulk to emulsion polymerization reactions. And I have elaborated a little bit of the polymerization reactions in this case. Now, I have exemplified the chain cross polymerization reactions, but most of the step cross polymerization reactions, condensation polymerizations, okay, are made by solution polymerization reactions. Solution polymerization reactions. You need to have a solvent, whether it is a water or whether it is a solvent. Then you have to follow those solution polymerization reactions in the case of condensation polymerization. But in the case of chain cross polymerization reactions, you need to choose at least one of four those polymerization processes. Okay? Mostly the emulsion or solution are your perhaps the option in the laboratory, the polymer synthesis processes. So these are the simple the introduction of the polymerization processes about the polymers, and you can take a look at a little bit more details about each polymerization processes in the textbook when you take a look at those. Depending upon the type of your emulsion polymerization reactions, you have several steps. You may have a nuclei or nucleation, where you have a monomer embedded inside of those micelles, and initiator is coming in to form the polymer and growth, and monomer was finishing, and so that you have a little bit of emergent type of the polymers in this case. Usually the droplet size are becoming bigger, starting from very small, becoming bigger as your polymerization is proceeded. Okay? So this is the introduction of the polymerization processes. What I can tell you finally in this next stage is that I wanted to introduce you about application of the polymers. Okay? Application of those polymers. Once you make the polymer, okay, we can apply those polymers to many areas, which is very useful in this case. Okay? I have shown you some of the fibers, some of the films at the beginning of the class, okay? And some of those fibers and films are not burning at all, even if I will use my burner to ignite them, so that I have introduced you that the fabrics could be utilized to form protective clothing or films for electronics industry and so on. So I just wanted to show you in a little bit more details about the application of those polymers in some of the areas that I'm familiar with. Okay? So once you make the polymer, whether you can make the polymer from your condensation polymerization or chain cross polymerization reaction, then you can make the polymer into a very thin film form and can be functionalized them so that we can use those in many of the other applications. And I just wanted to introduce you those polymers in the environmental application and energy applications. Perhaps you know the ion exchange membranes. Ion exchange membranes are in the form of the polymer containing some ions in there. Okay? If you have negatively charged ions, such as sulfonic acid group, into your polymer, okay, or carboxylic acid group into your polymer, then you have a SO3 minus and H plus, or COO minus and H plus form, right? So you have an anion at the end of a chain, whereas the proton is the counter ion in this case. Okay? Now because you have anion, we call this type of the ion exchange membrane as an cation exchange membrane. Okay? Cation exchange membrane, because cations could be exchanged. Okay? Although you have a negatively charged anion in the backbone of your polymer, we do not call this as an anion exchange membrane, okay? But it's a cation exchange membrane. So it's a little bit complicated and a little bit confusing. Okay, this is the cation exchange membrane. And this is anion exchange membrane. Okay, so cation exchange membrane has anion in the backbone or a little bit of side chain. Okay, so don't be confused. Don't be confused about the exchange. Exchange means that your cation such as sodium or the potassium will be exchanged. Therefore, cation will be exchanged. In this case, perhaps anion will be exchanged because you have positively charged the cation is attached here in this case. So we have our ion exchange membrane or ion exchange resin. You even have you can make the film form, which we call as a membrane, or if it's a resin, if it's a particle, we call that as a resin. Okay, in that case, cation exchange resin or anion exchange resin. Resin is a particle, in the case of particle, and membrane is in the film form. Okay? So those, I will talk about the film form. Okay, so ion exchange, the polymer is fabricated into the film, and you can make those films for exchanging those cations or anions depending upon your type of your the anions, so that you can make the sodium chloride using those ion exchange membranes. Well, sodium chloride salt could be easily fabricated. You can make it very simple, evaporation of the water or your seawater, right? But the high quality sodium chloride or even the energy could be obtained from the process. And also you can make in the chemical industry, if you wanted to make the chlorine, Cl2, okay, Cl2, not just a sodium chloride, but Cl2, you have to go through with those ion exchange membrane processes, okay, containing the cation and anion, stuff like that. It was stacked into a big tank, and if you put the sodium, the seawater, then you can produce the Cl2 and also the sodium, and even you can make the lithium from the seawater. Okay, it's not easy process, but you can extract those very precious metal from the seawater as well. So those exchange of those cations and anions is a big industry in using those ion exchange membranes. You can use those ion exchange membranes in the energy system, such as the fuel cell vehicles. So I just wanted to introduce you what is the fuel cell membranes. Okay, and I'm just going to introduce you about the, if possible, energy harvesting systems, because you are working on the energy. Okay, energy harvesting system using those ion exchange membranes. The other area about this using the environmental application of those polymers is the gas separation membranes, where I'm measuring in, so that I can show you some of those applications. So membrane is a very thin film. It's a very thin film, just like a film that you can see. But those films, if you use just the films, okay, excuse me, if you use just these films and make this folder, there is no function. There is no function. This film made of PET perhaps, or polypropylene. Okay, polypropylene is used just for taking your notes. I mean, taking your the papers inside of those films, right? He's worrying about something that I wanted to see him inside. Okay, so that you can print it out, of course, and I showed you that how you will make this film functional to the ink printing coating, right? So that once we make the polypropylene film and corona discharge those films and ship it to the other company, then you can print this out, right? But there is no function. Okay? In other words, if I wanted to have a mixture of the oxygen and nitrogen, such as in the air, okay, we can all breathe our air, right? You have a nitrogen and you have oxygen. 21% of the air is composed of oxygen, and the 79% is nitrogen. Size of oxygen is about 3.46 Armstrong, 3.46, whereas nitrogen is a 3.64. 4 and 6 is flip over. So you have only about 5% difference between the size of those oxygen and nitrogen. But if we do not have any oxygen supplied to the body, we are in trouble, right? If we have rich in nitrogen in our body, okay, just like the divers in Jindo, they experience a lot of the concentrated nitrogen in their body, and they're in trouble. Okay? Once you go in. So oxygen is very important. Then if there is any film, okay, and can only go smaller oxygen through those films, and nitrogen is blocked, you can concentrate those oxygens and can supply to the divers in there, okay? Or to the patients who are in the hospitals, just like President Igor Ni, okay? He's lying in the hospital, and perhaps he's wearing his oxygen mask, okay? So oxygen could be produced from the air using those films, okay? Using those films, not this film, okay? Not this film, perhaps, but if there is a film which can separate those gas molecules, it will be nice. Perhaps if we have any films with the nitrogen and CO2, size of the CO2 is about 3.3 Armstrong. Nitrogen again is a 3.64. So you have about 10% difference. So CO2 separation is easier than oxygen separation, right? So that you can take those CO2 out of those films. Or if you have a sodium chloride and water, sodium chloride, the size of those sodium chloride, sodium ion and chloride ion is about 7 to 8 Armstrong if it's hydrated, okay? If it's hydrated, 7 Armstrong, for example. The water is a 2.8 Armstrong, so it's pretty big size difference. So it's much easier to go the water through those films rather than sodium chloride. So sodium chloride will be rejected. So you can make the pure water out of the seawater, okay? So there is a big program back in 1950s, okay, in California. They need a lot of water. And in desert like the Sahara and others, they need also a lot of water. Well, where they can get the water? Because they have very hot weather and no water supply from your surroundings. The only the resources they can get the water could be from the sea, because if you think about the globe world, about more than 80% of the surface of those globe is covered with the sea, okay? Where the 10 to 15% is only covered by the land. Okay? So we are living on those small lands, but 80%, more than 80%, or 85% is made of sea. Okay? But inside of those sea, only the fish can live, but not the mankind's. What about the sea? For the mankind's, can we live inside of those sea? Is a big issue at the time, and I just wanted to share those questions with you. Can we live inside of sea just like a fish? The answer is no at this point, but I hope that you can live because of the explosion of those populations. Okay? If we have more people, then there is not much place to live in the land, so that we may go to the space, or we may go to the sea and live like a fish. If we build a house inside of the sea, okay, if we build a house inside of the sea, then we can live there. Okay. just like a submarine, okay? If you have enough oxygen from there. Okay? Inside of the sea, we have a lot of oxygen as well, although it's dissolved in the water, okay? Because the water can take those oxygen, and although the concentration is not as high as in the air, you have enough oxygen there in the sea. Okay? So you can take the oxygen just like a fish, because a fish, if you think about the fish, they can take the oxygen, okay? They can take the oxygen from the water, and then they store their oxygen inside of what they call is a gill, Gill. 불에라는 거 있죠. Inside of those gill, they take those oxygen, right? And they can release those oxygen. And this film of those gill is a membrane. Is a film which is functional only to pass those oxygen through those gills. Okay? So if you can build a gill, large gill, okay, large gill made of those functional films, we can only take the oxygen from the sea and put it inside of those gill, and we can live, right? So there has been an experiment. There has been experiments. So if we can make artificial gill and put it into the swimming pool, right? Swimming pool, and put the oxygen in there, and perhaps you would like to go, but there might be something happening. So only the family that they can go inside those gill could be duck. So duck could be going inside those gill, and they tested. I think I have seen the video. Anyway, you can live inside of those stuff. Or can we live in the space? Okay, just like a spaceman. Well, you have seen a lot of stories where if we can have a lot of explosion of the population in our world, then we have to go outside of our world to the space. So there's a lot of space war going on here to occupy those spaces. If you think about the space, then you have in a closed environment, and you need oxygen, okay, where you can produce your oxygen, or whether you could carry your oxygen to the space or not. I think they should produce their oxygen from somewhere. They should produce the water, or rather than carrying those water into there. Okay? Anyway, you can separate the water out of those functional films. So the wastewater treatment is one of the processes, and if you can make a very functional film with ion exchange capacity, okay, ion exchange capacity. I think currently they are using this type of CM, so that the proton is exchanged. So they call this as a proton exchange membrane, okay. Or if you can use this type of anion exchange membrane, instead of the chlorine, the hydroxide, OH minus ion, could be exchanged. So we call that as alkaline fuel cells. So once you can make a functional film, only the protons can go through, so that you can make a proton exchange membrane and the fuel cell systems. So you can, because the proton is exchanged, the electron is left, so the electron will be used as an energy source. So you can make electricity out of those PMFC. And you can make the power and make the fuel cell vehicles. The last example that I can show you is energy harvesting system using those functional films. Once you have a film, functional film, then you have two water systems. One is the seawater containing sodium chloride, okay, with high concentration, like 3.58% sodium chloride, or 35,000 ppm of the sodium chloride in the water. Okay? So it's salty, right? 35,000 ppm or 3.58% sodium chloride in your seawater. Okay? And if you look at the river water, you do not have any sodium chloride. Very small amount. Let's say that this is a pure water. Okay? River water is pure water. And you have salt water, high concentration. So you have a chemical potential difference, right? You have a concentration difference and chemical potential differences between the seawater and the river water. So by using the concentration difference, we can, if we can use osmosis membrane, which is a functional film, functional membrane, then there is a water transport. Okay, so water is going, in the case of osmosis, water is going from, river water to the seawater because of the high chemical potential from the river water side. So this is osmosis phenomena. But if you add the pressure higher than osmotic pressure difference from the to the seawater side, the water is passing reverse direction to the osmosis direction, so that we call this as a reverse osmosis process. Okay? We call this membrane as a reverse osmosis membrane. That's why RO, 역삼투, RO process is all about. That's why you're using the RO membrane to separate the water from the seawater, okay? Using the RO process. Okay, so by using the osmosis process, water is flowing from the river water to the seawater side, so that water flow is very fast. So during those the process, you put the turbine, okay, mechanical turbines. So the mechanical turbine will be moving because of the high flux of those water flow. So you move your turbines and get the energy, just like a hydraulic processes. That's why that's what we call the energy harvesting membranes. That's what they call the pressure retarded osmosis process, which is a little difficult. Or we can make the proton exchange membrane for the electrodialysis, and using those what they call is reverse electrodialysis, we can also generate the electricity from those electro-osmosis process. So these are the little bit of introduction about the thin polymer film, but was functionalized to make those the films for many applications, like energy application and the separation applications of the smaller gas molecules and smaller water molecules. You can make the film. You can make a polymer synthesis process, okay, in the laboratory. Perhaps you have seen those. You have already gone over to the polymer synthesis in your upstairs, the experimental class. You can make a polystyrene. You can make the polyamide. You can make a polyimide using the synthesis procedures. Okay. You put the monomer and filter them and so on. And then molecular simulation. Okay. And then you can dissolve your polymer into the solvent and put on top of your glass plate and cast a film. Okay, in other words, you make a film and evaporate those solvents and make a film, and then test it for the gas or the pressure retarded osmosis or fuel cells. So all of those facilities are in our the 9th floor, so you can see those facilities, and and also dissolve those films, dissolve those solutions, and make the hollow fiber. You can spin the fiber, or you can electrospun and make the mat, the non-woven mat, just like a film, and use those into many of those applications. Okay? We have other characterization, the instruments for all of those membrane evaluations and so on. So let me briefly introduce you about, first of all, the gas separation, the membranes. If you look at the natural gas, if you think about the natural gas usually is coming from the gas well, and it usually contains the CO2 and methane. Okay? Or if you go to the Kimpo Meripji, Kimpo waste factory, then they produce biogas. And if you go to the countryside, there's a lot of cow or animal cultivating houses, 축산농가 같은 cultivating houses. They produce a lot of biogases as well. Those biogases or natural gas, they all contain CO2 and methane. CO2 concentration is about around 15%, and methane is about 80 to 85% of those. The biogas or natural gas is composed of those anyway, mainly from the CO2 and methane. Size of those CO2 is about 3.3 Armstrong. 3.3 Armstrong. It's more acidic. Rather than alkaline. Whereas methane is a flammable. Okay, CO2 is not flammable, but methane is a flammable. That's why we use this methane as a fuel. Size of those methane, they have to put CH4. Methane, size of those methane is about 3.8 Armstrong. 3.3 and 3.8 Armstrong. So only about 0.5 Armstrong difference. So about 15% difference between those, the size of those two molecules. Which is more easier to pass through, CO2 or methane? CO2, of course, right? CO2 is a smaller gas, and smaller gas, so the CO2 can pass through those much easier. But we have the polymer traditionally, such as a polysulfone. Polysulfone contains aromatic rings and the sulfone groups, SO2 groups, right? Polyether sulfone or polysulfone has SO2 groups. Those polysulfone has long been used for separating those CO2 and methane. But this polysulfone, the cavity size of those, the pore is only about 2.8 Armstrong. If you think about 2.8 Armstrong pore here, and have a 3.3 Armstrong and 3.8 Armstrong gas molecules, it's too small. Too small the size to pass those CO2 go through, right? Therefore, what they have done was that they have to pressurize those CO2 and biogas or methane gas up to about 20 bar, 20 atmosphere, okay, high pressure, so that only small gas molecules like a CO2 can diffuse, okay, diffuse through, just like jump okay, in one pocket to the other pockets, just like what you have looked at in your physical chemistry textbook, okay, jump, diffusion, but you can do that, but the permeation rate, transport rate is very small because of very small gas, very small the pore size, right? If we can open those cavity size, pore size, from 2.8 Armstrong to about 3.3 to 3.5 Armstrong, okay, just right for CO2, then I think we can only pass the CO2, but methane cannot. Methane is too large to go through those 3.3 to 3.5 Armstrong cavities, but 2.8 Armstrong is too small. Okay? So if we can open a little bit and just right for the small gas molecules, okay, then we can have a very high flux. And that's why what we have done, in this case, and the polymer was made from the polyimide to polybenzoxazole, and therefore we have about several hundred times larger flux for only for CO2, and also for oxygen from the air, okay, oxygen from the air, and hydrogen from CO2, and so on, depending upon the chemistry, and we have been very successful to separate those molecules. What we have achieved was that we found that this cavity, this pore, is in two sizes. What they call is a bimodal distribution of those cavity sizes. We have a smaller cavities and larger cavities, just like hourglass. 뭐라고 그러지 이거? Hourglass. 모래시계. Hourglass. So we have small cavity size is about 3.5 Armstrong. Large cavity size is about 8 Armstrong. The large cavity size doesn't matter for the selectivity, where it could be contributed to the permeability, so that we were very successful to get a very high flux of CO2 molecule or hydrogen molecule, depending upon the cavity sizes. And we are working on with the nitrogen and methane as well, and oxygen from the air, stuff like that. So this is one example. What we call is a TL polymer. TL polymer is the one that when you make the precursor polymer and thermally treated them at high temperature, then you can rearrange the functional groups to become another functional group. So what we call is a thermally rearranged polymer, membrane. Okay? And this was the world first, the TL polymer membrane. It's the Hanyang University is a mecca of TL polymer membrane. Although TL polymer itself is not made from Hanyang University at the first time, but was first made back in 1966 by Russian chemists. Okay, and they published this similar concept back in 1966 in Russian polymer journal, but was repeated by the American professor Matthias at the University of Southern Mississippi back in 1999. Okay? And they published 2 papers with this concept, with this chemistry, back in 1999. And they reconfirmed their 1966 Russian discovery, okay, first discovery, and repeated their experiments, and they published 2 papers in 1999. But they did not realize the cavity sizes for these separations. They just did the chemistry itself, okay, in 1966 and 1999, But in 2007, we did this for membrane, and we realized the size of this is very different from the previously reported polysulfones and polyimide membranes, and that's why we were successful to get these publications. Later on, we after we started our TL polymer concept, the other group in UK, England, they did the polymers with the intrinsic micro porosity. I think there. Okay, this is very similar. This is very similar structure here. They contain some of the spiral, what we call is the spiral units, and this is spiral unit containing polymer was introduced in 2004, about 2 or 3 years before our discoveries of TL polymers, and they were in England. They are the mecca of PIM polymer. Okay, Hanyang University is a mecca of TL polymer. Whereas the PIM polymer was made first by the researchers at 2 universities. One is the Manchester University and the Cardiff University. Perhaps you have heard about the Manchester and Cardiff, right? If you are familiar with the soccer, right? Football or soccer. So Cardiff and Manchester collaborated each other to be successful to make the PIM polymer. But later on, I think they have developed some of the other membranes. What we have done was that what if we combine the TL concept and PIM concept so that we make a spiral or PIM and TL polymer, and it was successful last year to get this type of spiral units containing the TL or penzoxazole concept by the TL concept. Okay? And this is quite successful to get it now. And last year as well, we also commented on their the other concepts like very rigid structure with the bicyclic rings. The polymer is a, if you think about the leather polymer, 사다리, leather polymer, you have aromatic rings fused to each other, okay, just like a leather. And if you take a look at this structure, it's like a leather, right? It's like a leather, where you have a bicyclic leather. You have a leather, but one of those leather is linked together again. You have 2 cycles in one ring, in some cases. So bicyclic ring was here, and they have published another article in the same volume, but we are lucky to comment on what they have done. Okay? So we analyzed that rigidity, okay? High rigidity of those leather polymer or PIM polymer with the other bicyclic ring is a cause of those the high fraction free volume and achieved a very high permeability, particularly to hydrogen, okay, separation, and was very honored to publish those perspective articles in this journal. And very recently, I mean in this month, May, we have hired a Chinese postdoc who can make the very similar to this structure, containing this structure and polyimide structure, and we were successful to get those what they call is a Trago space polymer containing bicyclic rings with imide structure. So we were successful to get a very high the productivity of those polymers, and was published online yesterday, and will be published in May 27, which is next week or the week after next week. Anyway, at the end of this month, will be published anyway. So this is the evolution of the TL polymer concept. TL polymer concept with the polybenzoxazoles for separating small gas molecules, not larger gas molecules, but small gas molecules in the size of 2.8 Armstrong to about 3.8 Armstrong. Okay, those small molecules can be separated by tuning the cavities. Okay, and then we can fabricate them. Now this was I told you that Hanyang University is a mecca of TL polymer, and we have published so far about 20 papers for the last 4 years about this TL polymer, and the people in the world are following our TL concept, and including our papers, about 50 or 55 papers were published so far for the last 3 or 4 years. So they are following our concept, and they would like to learn and duplicate our TL concept, and it's my pleasure to provide the information to them, although it might be a little bit of confidential in some cases. So we license this technology to the company in America, and they are producing the hollow fibers for gas separations. You can make this polymer. Okay, once you've synthesized those precursor polymer, then you dissolve your polymer and can cast them, or can make the fiber out of those. I think I showed those hollow fiber systems. If you're not, then I think we can go there. It's just right across this hall. And you can dissolve this polymer and put it into the very small bath, and just like a pencil, okay, ballpoint pen. Ballpoint pen has a hole. If you take those the pencil out, then you have a very small hole. So this hole is filled with a polymer solution, and if you pressurize them, polymer solution will be going through those holes, small holes. Right? So polymer solution is going through those holes and put it into a coagulation bath, which consists of water. Then the water will coagulate or precipitate those polymer solution. So there is an exchange between the solvent and non-solvent, and can make the fiber. And this is the consequence of the fibers. So once back there, you have a polymer solution, and push them to the water, and the water will make this polymer solution, the transparent solution, into the white, milky, the polymer precipitate, and this becomes a fiber. And you can take this out, and this is the precursor form. And after thermal rearrangement process, you can make a little bit dark, the TL-PBO membrane. And of course, you can make a hole inside of those fiber by pushing the water. There are 2 nozzles, and the water is injected as well as the polymer solution. And therefore, you make a hollow fiber. You make a small hole inside, but the outside of those the fiber is very thin skin. So this skin is acting as a selective layer, whereas a sponge layer, sponge-like structure surrounding this skin is acting as a mechanical support. Okay? Not acting as a selective layer, but it's a mechanical support. So you can make a hollow fiber, and if you put several hundred or several thousand fibers inside of those tubes, then you can make what we call is a module. Okay, we can make a module out of those fibers. If you can cut those fibers and put it into those the modules, you can use this module for your industrial separation processes to separate the air, to get the oxygen, to separate the biogas, or to separate the of course air to get the nitrogen, okay? Oxygen or nitrogens. And the company that we are working on is trying to use the module for the airplane, okay, for the airplane. Okay? If you think about the airplane, airplane has a fuel tank, right? Fuel tank. If you have a fuel tank, you consume the fuels, of course, right? Once it was filled, there is no water, fuel vapors, but as you consume your fuels, then you have empty spaces. So those empty spaces are filled with the fuel vapor because of the vaporization of those gasolines or jet fuels. Okay? Those vaporized fuels will be very harmful, very harmful if there is any spark. Okay? If there is any electrical spark is there inside of the fuel tank. And you have seen a lot of those explosion of those the vaporized fuels in the gas stations, okay, fuel stations. The explosion was, I remember, was nearby Suwon, okay, and I think there's a lot of explosion in Korea right now because the gas storage tank was filled with the with other the unlawful gases, gasolines, and there's a lot of explosions because of a spark. If there is a spark to the vaporized the fuels, then there's a problem. In fact, in 1999, there was an airplane explosion. When the airplane was flying from U.S. to Europe, and in between those, the Atlantic Sea, there was a big explosion, and everybody was gone, died because of the spark, okay? And during those the airplane fuel tank. And if you supply the nitrogen gas, if you supply the nitrogen gas to the fuel tank, you can inert. You can inerting, or what we call is a blanketing. Blanketing. If you supply the nitrogen gas into the fuel tank, you can blanketing those fuel tank so that there is no explosion. Okay? These type of modules could be, and every airplane after this explosion in 1998, every airplane produced after that explosion, such as a Boeing or Airbus, they have to be equipped with this type of modules. And every airplane which was produced before the explosion, flying over to U.S. air, should be equipped with this type of modules. And this is a big business there, although in Korea it's not known. So that the company that we are working is very eager to produce the type of modules because this is very effective. Effective in terms of the permeance or flux. So flux, if you have a high flux, then you do not need to have a big modules, but if you can have the small module for the same efficiency. Right now, the 747, Boeing 747, need to have a big module I think they have to have about at least 10 modules with a big size to supply those blanketing nitrogen gas to a fuel tank right now. Okay? The weight of those big module is pretty large, pretty heavy, so they wanted to replace those modules with these smaller modules. Okay? If there is any very high separation efficiency of those membranes. I think with that, I can stop here. This is just a small example of what we can achieve, what we can apply those polymers for one of the applications.